Okay, so this is recording I am doing at home, and this is the best way I could see to kind of write along with the notes and explain a little bit more. So obviously we're talking about compounds, and in Unit 7 we started talking about ions and covalently bonded molecules, and you would see that in some situations we would have maybe one of one element and two of another element, or one of one element and one of another. So those would be compounds. Right here we talk about that elements having different properties than the individual elements themselves. So for example, I always say this in class about sodium and chlorine, NaCl. Sodium metal reacts violently with water. Chlorine gas is very deadly. If you put them together, they form table salt. So obviously, the properties of the combined elements are different than each one individually. Okay. Now here are some examples. You can see my finger. I don't know, it's kind of weird to see that. But you can see some examples of compounds. Another one would be like H2O2. That's hydrogen peroxide, like peroxide that you find in a cupboard to clean out cuts maybe, or whatever you use it for. But there's all kind of compounds. CO2 would be another one that is very common. Carbon dioxide. Carbon monoxide is another one. All right, so next one. Now, in another set of notes, we talked about the octet rule, and I believe that was when we still had class together, how the magic number is 8. So whenever we have something like, let's say, boron, okay, or let's go lithium. Lithium has 3 protons and 3 electrons, and so that would be neutral. But neutral doesn't mean stable. So if you recall, it'd have a single dot next to it, 1 valence electrons in the very first column, and it would lose that to another element, and it would form a cation, 1+ cation. Okay, so the reason we're losing or giving up this electron is to get stable. Okay, stability happens when they react with other elements. All right. Down here, law of constant proportions. So what that means is if we have H2O and that's water, then it's always going to be H2O. Okay, it's not going to be like H4O2 or something like that. Okay, we can't have maybe like an H3O and say, well, we'll just get rid of one of these hydrogens and it will become, that doesn't work, okay? So it always has the same proportions. Same thing up here. Well, I guess it was on the other paper where I had carbon dioxide. Carbon dioxide is always going to be written with these proportions. 1 carbon, 2 oxygens. So now we're getting into the actual formulas here. And I kind of already drew a couple. You saw some examples. And I mentioned this in the last slide. It talks here in the subscripts. The subscripts show the number of each atom. Okay, the number of each element. The atoms of each element, I guess we could say. So in this case, you notice there's no numbers here. Technically, it'd be a 1 and a 1, but we don't write that. It's not necessary. So if there's no subscript, we know it's 1 atom of that element. Down here, obviously, we'd have 2 sodiums, and then we have 1 sulfur. This next part is something that I'm not saying we're not going to focus a lot on, but we're not, okay? Or that it's not important, but we are going to focus just a little bit on it, all right? So go ahead and write these notes. And there'll be some pictures on the next slides. The one thing I want to point out is right here. where it says longer bonds are weaker. So basically, if we have something that's further apart, the attraction between them two would be less than the attraction if they were closer. Think about it. If this is more attracted to this one, they're going to stay closer together. So that makes sense. This would have a stronger bond. This one would be a weaker bond. I hope you could see that on my screen on the iPad. I'm not sure you could see it. There we go. Next, here's a couple pictures. Okay, it's just to give you an idea about the distance between the two. So we have fluorine and chlorine. And obviously you could see here that the fluorine is closer together, meaning it's a stronger bond. Okay. Now if we look at the periodic table, look at where fluorine's at, and then chlorine, bromine, and iodine. And see if you could make a determination about what happens as you go either up or down a column on the periodic table as far as the bond length. And here is an example of the bond angle. Okay. Bond length, bond angle. The angle between the different atoms. This one's a little bit harder to see up here. This says NH3. So it's 1 nitrogen and 3 helium. Well, I don't know why I made that a big 3. Little 3 there. 3 heliums. 1 nitrogen, 3 hydrogens. Okay. And so the bond angle would be if we make this like triangle. Just like in math class, geometry. Okay. These would be the angles. And it's supposed to be 3-dimensional. Now down here, this is where we're going to have to remember these. Okay. So linear means there's 180 degrees between the two bond lengths. Okay. Trigonal planar, I always imagine if we had like 3 balloons that look like this, and we held them all like in our pinky, how would they separate? Okay. They would all have 120 degrees. Now remember in math class, 120 plus 120 plus 120 would be 360. If you notice, this says planar because it'd be like laying flat on a plane. There would be no really like 3 dimensions to it. Tetrahedral would be if you held 4 balloons. It's hard, I can't even draw that, but this is like more of a 3-dimensional thing. So we would have 1 this way, 1 that way, 1 this way, and then 1 bond length coming straight up. Okay. Obviously, here's our angle. All right, chemical structure. Now we're getting into a little bit more of what we maybe had already gone over about anions and cations and that sort of thing. Right. So, solids. They have high melting points, boiling points, networks of bonded ions result in strong positive and negative attractions. For example, sodium chloride. So if you notice, sodium is on the far left. This is our metal. And chlorine, which is always a salt, it's called a salt. Now, I think a lot of times whenever anybody hears a salt, they think of table salt. But look, this is a negative ion, a non-metal found on the right side of the periodic table. Okay. So this is for our ionic bonds, okay? Now our covalent bonds, or our molecules, and the attraction is weaker than networks. Remember that in molecules, covalent bonding, we're sharing electrons. In the ionic bonding, we're actually giving up and receiving electrons. Okay, here we go. Ionic bonds. One loses, the metal loses and the nonmetals gain. For example, up here, our sodium chloride, remember that sodium is the +1 and chlorine is the 1-. Solids at room temperature, high melting points and boiling points. Obviously dissolve in water, and I could keep reading to you, but I don't think that's necessary. Okay. This neutral charge is extremely important. When they become stable by either losing or gaining electrons, if you think about when they combine together, they will still be neutral, right? Because we have one plus and we have one, and we have one negative. If we were to add those up, it'd be neutral, 0. And here's a good one too. They do conduct electricity when dissolved in H2O. So I'm not saying anybody should do this, and you'll find this in many videos, so I don't feel like I can't say it. But if we had distilled water where there was no ions in there, it should not conduct electricity. All right. So you could probably find a video on YouTube where they have deionized water and they will have electrodes going into it, and the light bulb on the other end will not light up. Okay. Like there'll be a separation of electrodes. So maybe here's your light bulb over here, and then this side will be hooked to the electricity. And if there's no ions, this bulb will not light up. But if it's ions, if we poured table salt in there, this light would turn on because it's able to conduct electricity through it. And that's what it's talking about right here. All right, now our covalent compounds. Already mentioned polar and nonpolar. Okay. So the most common one, H2O for polar. Right? Polar means that one side is generally more positive or negative than the other side. Okay. And you could look back at other notes that we put on the board about that. One thing you'll hear very commonly is that likes dissolve likes. Years back, I had a pen, and I stood on a table, and I drew the pen on my pant leg. And I tried to get it off with water, and water wouldn't take it off. And the reason was the pen was nonpolar, and the water is polar, so that it would not dissolve. It would not take it out. I need to use a nonpolar substance to remove it, and I put it in isopropyl alcohol during class, and I realized it wasn't coming out, so I actually had to go home and soak it, and then it made this big blue ring and it ruined the pants. But anyway, the whole point is that polar dissolves polar things, nonpolar dissolves nonpolar things. One big important thing here about covalent is that we're always talking about nonmetals. So when we have the periodic table, right, however it looks, something like that, the nonmetals are always over here, and the metals are everywhere else. So there's a very small portion here of nonmetals that we use for covalent bonding. Okay, that's the end of the notes.